Yeah, we can go to the keynote presentations. So first, let's welcome Professor Colosimo.
Furthermore, in biomedical and also in aerospace, the zero defect is a must, it's not an option. And the other issue is that additive manufacturing allows customization. So it means that each new part is different from the previous one. So we cannot take advantage of repeating over and over the same product and same process, but we need to be able to adapt the process depending what is the specific part we are producing. This is just the ASTM report that was out last year from ASTM and NASA. That is exactly pushing a lot of emphasis on why in situ monitoring in additive manufacturing can be very promising. I will just briefly show that it's not just a matter of data, it's also a matter of process and data gathering, which means sensors, because all these aspects are quite strongly connected in order to do a good job. And being able to move from, let's say, in situ monitoring, that is just taking data, to, let's say, intelligent machine, which means having one machine that is able to take advantage of the data. In that specific, let's say, picture, it's shown all the different levels we can use for monitoring and having information. Level 0 means just sensors, signals, like pressure, power, and all this type of stuff. I will spend most of my time on level 0 and level 1, which means image-based, augmented, let's say, additive manufacturing monitoring. But you can even go a little bit farther in trying to have data on the melt, which is the zone in which the beam is melting the powder and so doing his job of producing the part. And also even there's a new direction going beneath the layers, so something that you cannot see, but it's below, let's say, the level that you are processing. There is no level 0, because unfortunately something can happen even if you're producing the part layer by layer. If you look to all the products that you can produce with additive manufacturing, it can be really amazing in terms of, let's say, the different sizes, different material you can process and produce. You'll see a lot of applications going from implants, which means biomedical implants, to jewelry and creative industries that are, quite good here in Italy, but also automotive and racing, or even tooling and molding, which is quite interesting direction. So all these channels that you can see in different colors represent some internal channel that can be just produced by additive manufacturing and are following the surface of the mold. By following the surface, you can subtract heat just where it is needed. And this means that you can be quite more effective in producing parts thanks to this mold that have these conformal cooling channels. This is just, since we are in Italy, also 3D printed pasta. I think it's quite interesting all the direction that 3D printing is taking in terms of food industry. And there's also some connection on bioprinting with the food industry, because you know that cultivated meat can be even 3D bioprinted. So moving to why vision is so important and data are so important in this case. We have been spending most of our, let's say, effort in the last years trying to avoid basically defects. And these are a lot of defects that can arise in parts. Since, as I was just showing, all this part at complex shape, this is what is really, let's say, common point in all parts that are 3D printed. Unfortunately, complexity means that you can have a lot of defects, which are geometrical and dimensional defects. You can have even small cracks or some sort of thermal stress that are creating some change of the final shape. Unfortunately, you can have even small defects inside the part that are called porosity due to excessive melting or insufficient energy while we're melting. And these are unfortunately big enemy of the mechanical performances at the end. And I will also spend some time on the new direction that is going in the direction of microstructure tuning. Microstructure means that all the colors that you see are grain inside the part. And depending on the size and the orientation of this grain, you can have quite different mechanical performances at the end. So tuning the microstructure, which is due to the way in which you are melting and cooling the part, this is going to affect the mechanical performances at the end. What is the paradigm shift? Instead of just waiting all the time at the end to have the final products, the key point is that you want to move from product data product quality data to process data. So it means putting a lot of sensors on the machine, take advantage of all this data and being able to detect the defect as soon as it happens, or even avoid the defect to happen if you see that something wrong is happening. And as we say, you can take a lot of signals, you can take image with the visible and thermal range, but also you can take advantage of the dynamic that you can see while the process is running. These are some examples of things we have been doing and publishing. Actually, in the literature, you'll see a lot of work from my group. The first, and then we'll spend some time on this, it's just taking a picture, since the process additive, it's happening layer-wise. So at each layer, you can take a picture and trying to investigate what is the shape at that layer that has been melting, and trying to see if this final shape it's coincident or has some discrepancy with respect to the nominal shape. So it's some sort of quality inspection layer-wise, just by comparing what is the melted zone with respect to the nominal zone, so the nominal shape, and being able to detect as soon as possible some discrepancy that can result in the final defect of the part. Clearly, I will not have enough time just to describe, but there's a lot of, let's say, papers we have been trying to, let's say, write on this direction of video image, in which the main job is to find hot spot and cold spot. Hot spot means spot that remains hot for a long time, and you will see that while the laser is doing its job of melting, when it stops in one specific corner, this corner remains with high intensity for a long time, and this is going to be a defect. So again, by detecting this hot spot in real time, this can create advantage. Sputtering is a quite interesting phenomenon. And again, there's a lot of research going on in trying to investigate on the shape of all these sputters that are coming out from the melt. Depending on the type of sputter signature, you can have porosity at the end. And we've been also spending some time in moving from monitoring to automatic control. So once I see something is wrong in the layer, I can even react and compensate with the process parameters in the next layer just to heal, let's say, the product while it is machined. There are some new directions also that we are interested in, like roughness prediction via thermal imaging, and I will say some word on in situ data mining for microstructure prediction. So I will focus my talk on geometrical deviation, how to take advantage and why AI is so important in this direction, and then I will spend some time in the microstructure prediction. Let me just start with a very complex shape that you can produce with additive and only with additive manufacturing. These are called lattice structure or metamaterial. You see that you can create structure that are full of voids, that at the end have the same mechanical performance, the same stiffness as fully dense part. But clearly there's a lot of degrees of freedom in the way in which you are designing this part of the website, but also in the way in which you are producing. So what we have been doing is just taking image in real time from the machine that is producing this lattice structure layer by layer. And we have been developing some solutions that are able to detect layer by layer the nominal, let's say the actual shape of the melted zone. In this case, you are just seeing a video that is showing each layer and the detection algorithm that is able to detect what is melted with respect to the loose powder. And so it's basically able to detect the geometry of the lattice structure at that specific layer. There's a lot of pain because each layer is different from the previous one, unfortunately. So it's not that you can tune the algorithm one layer and that's it for all the, let's say, job, because unfortunately, depending on the scale strategy and the illumination condition, you can have a lot of difference layer by layer. And so you can kind of tune the edge detection algorithm depending on the fact that you are in dark field image or bright field image. The end of the story is that if you're good enough in doing this job in situ and in line, you can be quite, let's say, impressively good in, let's say, detecting the final shape, the final geometry, with respect to what you can do ex situ at the end, which is to ask the ground truth, and is done by X-ray CT, because X-ray CT is the only way to qualify the part at the end. And this is just the, let's say, final performance on how good we are in detecting the final shape of the lattice structure at each layer with respect to what is the reality that is measured ex situ via X-ray CT. With our, let's say, weighted B-spline solution, we are able to have in situ and in line a deviation from the real measurement that is done ex situ, which is quite negligible. It's 0.05%. What we've been trying to do also, together with the ESA, European Space Agency, the project that is trying to investigate how the defect size is affecting our capacity in detecting the defect. This is a real workpiece for, let's say, in a space application in which there's a small defect, as you can see, created on particles while we're melting. All these, let's say, dark side is the melted area. All this gray side is the loose powder. We want to recognize the shape of this, the final, let's say, melted zone. And there's one small angle that is missing over there. So this is a defect. We have been trying to change the size of the defect and trying to investigate what is the probability of detecting this defect in situ and in line layer wise. As you can see, the three different curves depend on the type of machine you are using. For instance, the blue one, it's a machine that is a commercial machine with a camera that is mounted on, that is a standard one. The red, it's our machine that has been a little bit tuned to have a better resolution in detecting the image and also to have some sort of good illumination condition. And so the probability of detecting the detection, depending on the defect size, means that if you're using the standard machine, you can be quite, let's say, make a good job only when the defect size is large enough. If you're using some sort of trick, one existing machine, you can be quite more effective in having a high probability of detecting sizes of defects that are smaller. The last one, the green solution, is a solution which we have been also changing the sensor. We have been developing a new sensor because, again, data mining is not just the matter of the algorithm, it's not just the matter of the machine, it's also the matter of the sensor, so the glasses that you have on your machine to be able to detect the defect. And this is our, let's say, new solution that we have been patenting that is called ScanIt. Basically, this is a CMIS sensor that is mounted on the recorder. The recorder is just spreading the power. As you see, after the laser has been doing his job, thanks to this sensor, that is a scanner, basically mounted on the recorder system, we are able to basically have a good high-resolution image of the melted zone. And going back, we can even say something on how the spreading, so the powder has been spread, if this is uniform enough. I can just show the difference between having, let's say, traditional camera solution. In each image, it's the left-hand side. So you can see that the resolution is not good enough, especially if you have tiny parts and pillars produced. On the other side, in the same image, on the right-hand side, you see our scanning sensor, how good is in detecting deviation. And even in the blue, let's say, rectangular, you can see that we can appreciate some sort of texture that is quite important. So how good it's the melted zone, if the roughness is in the melted zone, it's good enough or not. So my first key message is that you need to know a lot about the process. Clearly not the same person, but there's really the need of a multidisciplinary team. You need to develop new sensors, and you can add some good also solution for, let's say, doing data mining. You can place the game also in going with complex shape. We have been trying also to create some algorithm for 3D manifold, let's say, lattice structure, and also to investigate if you're using traditional extrusion-based solution, the one that you are used to, have a lot of, let's say, attention to some sort of random texture that sometimes can reveal some defect. And also in this case, we have been trying to investigate some new solution for image analysis to investigate this defect on some random textured surface. Just a few words on the last topic I want to mention, that is focusing on microstructure. Usually, additive allows you to tune the microstructure. This picture with all these colors and all this border looks quite just a nice picture, but what is happening is that they are saying something about the final mechanical performances of the part. So having some sort of, let's say, fine microstructure with a given orientation can bring some fatigue resistance or mechanical testing resistance at the end. While moving in the other direction, you can have some different mechanical performances. The good news is that by playing with process parameters with additive, you can tune the microstructure. So you can decide if you want to go in one direction or the other one. So this is an additional powerful solution. Unfortunately, most of the time, these microstructures are judged by eye. Just an operator is saying, okay, I see this type of microstructure, which is different from the previous one. But you see that classification in this case can be quite a complex task. What we have been doing, and this work has been done together with the teams by Professor Cameron at Georgia Tech. It's trying to, let's say, overcome the existing industrial practice in which there's a quality assessment based on the operator's experience of this microstructure classification. But we have been trying to develop some machine learning solution going in the direction of have some quantitative assessment. I will not go in deeper detail, but in case you are interested, there is a paper submitted that is exactly trying to understand how we can find all this color map of brain. The measurement system, it's called a VSD. And the way in which we have been doing the job, it's just trying of combining some way of classifying the feature in terms of dimension of brains and also the colors that say something about the orientation, trying to, let's say, reassume or find a way of describing these sizes and colors in one specific way, and then make some dimensional reduction and clustering. I will just show the results because I know I'm running out of time. Basically, results are just showing these are different microstructures we have been trying to classify and cluster. If you're using PCA, you can do not such a good job, but if you're using some different way of making dimensional reduction and then clustering, you can be quite effective in predicting and have some sort of good, let's say, capability of classifying different microstructure depending just on the image, with really a reduced amount also of training set. So I think that also the direction of going with complex data sets that are quite interesting for industry, it's going to be maybe the future of the connection between additive manufacturing and AI. Okay, conclusions. First of all, additive manufacturing has a lot of potential, let's say, directions for the future because it's a technology that combines digital. It's totally digital. You can just design the part and not the printer. So just transforming or sending a file on the one side. In the other side, I've been showing that you have a lot of information if you are able to put some sensors on the machine while the process is running. So it's really going in the data mining, let's say, direction. It's also supposed to be green because as I was showing, all the parts that you are producing are lightweight parts. So you are reducing the amount of material you are using. All the parts are reducing the fuel consumption if they are mounted in our airplanes. So this is why additive manufacturing has low potentials for the future. Clearly, if you want to combine digital and green, since at least in Europe, there's a lot of pressure going also in being sustainable, you need to take into account that the element you are using should not be so let's say, energy consuming solutions. As a matter of fact, if you go in terms of data size, just by taking video and image in very simple, let's say, printing, you can end up with really an amazing amount of data. So dimension reduction in terms also of what type of data you need to collect and what type of analysis you need to do, I think is the right way to go to combine sustainability on the one side and the digital capability on the other side. This is why there's a lot of interest, at least in terms of companies that are introducing this algorithm. We are working with Siemens in Germany on this direction. It's to have some sort of dietary data analysis. So it means I can just pick the data or try to summarize what is really important in the data instead of storing an amazing amount of data. And for instance, this is just an example that we have been playing with. Sputtering means just counting and have an idea of the amount of sputters that you can just have in real time. But if you are able to create some sort of recap of what is the signature of the sputter, maybe using some K function that is used for point processes in industrial statistics, you can just store a curve instead of all those data, video data that are representing the sputters, and this can create a significant reduction on the amount of data you can store. Eventually, there's a lot of attention, as the previous speaker was mentioning, about robustness and interpretability and physics data modeling, because all the company, in order to put all this, let's say, solution inside their machine, they want to better understand what's going on. They want this solution to be quite robust to false alarm. They are the big enemy of all this in situ quality data mining and data monitoring, and maybe bring all the knowledge that they have, the process already, let's say, somehow in the element, because there's a lot of know-how available in their, let's say, expert knowledge database. I think this is my last comment for today, and thank you for the attention.